Good afternoon, everyone. Today I will talk about the signal processing for Doppler-only passive Wi-Fi localization. And actually, this method is not limited to Doppler-only passive radar localization. And actually, I think it can apply to linear combination or nonlinear combination of different Doppler signals. And how do we separate them, and how do we estimate more accurate Doppler frequencies? And this work now has limited to the simulation data, and because mainly my work is in passive radar, so I use the Wi-Fi signal for the simulation. And here is the outline. First, I will introduce the motivation of localization using Wi-Fi radar. Basically, the motivation of this signal processing method. And second, So the second, I will introduce the simulation scenario descriptions. And the third, I will introduce the signal processing using the sparse signal recovery. And the next, I will introduce the signal processing using the joint sparse signal recovery and show whether the joint processing can be an advantage over the single sparse signal recovery method. Yeah, so first, there are several research questions for these simulations. Yeah, so the first is, in passive Wi-Fi radar system, is it feasible for the Doppler-only localization of moving human in a multi-static passive radar system? So before I guess, Carl has introduced a paper about if we know the initial point of one target, how can we use several, or two passive Wi-Fi receivers to estimate the Doppler of that target and do the tracking using the dead reckoning. And so my motivation is, shall we not use the initial point, and shall we use only the Dopplers to estimate the localization and the speed? Of course, this one should be applied to in the multi-static passive radar system. And the second question is, how shall we estimate the localization and velocity of targets? The third is, how shall we design the joint processing method? Because it is a multi-static passive radar system. Yeah, so here's the simulation scenario and the basic Doppler-only estimation model. First, indoor scenario is chosen with 6 meters by 8 meters. So here is the horizontal one is the x-axis, and the vertical one is the y-axis. And as we can see, there are 4 receivers here, and this is the transmitter. This is a very simple scenario, so just for proof or verification of the signal processing method. And the signal, we use the QPSK of the OFDM modulation, and the sample rate, we use 2 megahertz because the speed of the laptop, we cannot do 20 mega. Yeah. And then we use 0.2 seconds integration time for one Doppler estimation. Yeah, here is the Doppler-only localization model. So first, we should identify the moving state of the target, which is 4 variables, x, y, vx, and vy. And for the ith receiver out of the 4, these positions are xri and yri. And the transmitter location is xt and yt. Yeah, and we assume during these 0.2 seconds, the velocity and the position is constant. But if we lower the integration time, and this method also applies, and the distance from the target to the ith receiver, which is the dpi, and the distance from the target to the transmitter is dpi. It is very simple equations. Yeah, and the bistatic Doppler corresponding to ith receiver fpi can be represented as this equation. And then where c is the speed of light and fc is the frequency of the Wi-Fi signal. So here we use 2.426 gigahertz. Yeah, so suppose we have 4 FPI, and we need to estimate 4 variables, which are x, y, and the Vx and the Vy of that target. So how do we solve this problem? We could see that this equation is like a nonlinear one. So our aim is to solve the following nonlinear inverse problem. Yeah. So, and the most simple idea is, suppose we know the 4 Doppler exactly, which is P1, P2 to P4, and we might be able to solve the state of the target. But it is worthy noting that the Doppler estimation of each receiver, this is a nonlinear one. Yeah, so why are we not solving these nonlinear inverse problems? First, because it is a nonlinear one, and then there's no closed form solution, so we need some optimization method to solve this problem. And the second, it is because of the lack of the accuracies. Yeah, so our solution here is we transfer this nonlinear inverse problem to a semi-parameter linear problem, which is we introduce a dictionary corresponding to Doppler signals, which corresponds to different grades of the parameters. Here, the parameters are the 4 variables in the state of the target, which is x, y, vx, and vy. And we separate these 4 variables into grades. Yeah. And we make a dictionary of the Doppler signals that can be echoed from that particular grade. And then if we have that dictionary...
On that note, can the x and y, are they limited within bounds that you kind of know? Like x cannot beyond the edge of the room, and the velocity of the target, the person isn't going to walk 1,000 miles per second. He's normally between a certain range. Is that how you've narrowed the possible values?
Yeah, it should be a certain range. Okay. Yes, and so we divide the position limits and the velocity limits into grades, respectively. And we see the potential grades in this searching area. The next step is, so for example, for the ICE receiver, we set up a dictionary AI, and corresponding to m by n, this is the structure of that dictionary. And so n item corresponding to the respective grades. And m is the samples we obtain after the correlation at each grade, which means m is the samples of the echoes from one particular grade. And for the simpler case, we just use the item as the Fourier basis, which is this one. So here we have the dictionary A, and we would like to which grade is the target in exactly, which is the x here vector, and the y is the m samples we have got after the correlation or based on the reference signal multiplied by the Doppler. And so in this simulation, the grid size is, we put the grid size to 10, 10, and 5, and 5.
Can you calculate this grid offline then?
Yes, yes.
And then you're doing cross correlation to find which answers the most possible, most likely by correlating with this grid?
Yeah. Yeah, so we got the resolution based on these grades and the limits. And after, yes, so I neglect to mention that n is much larger than m. It is because if n is equals to m, it is the traditional FFT. And we want the super resolution, which is very feasible for this application, which is the localization within 0.2 seconds in an indoor environment. And because n is much larger than m, and we know in the vector x there are fewer targets than this whole grid, the number of grids. So we see X is sparse. So we see, we put this original problem into sparse signal recovery problem, and which can be solved by convex optimization algorithms. And here, the Y is the signals we collected, and A is the dictionary, X is, for example, which grid has the most power to combination of this Y. And here X1 norm means we want this X to be as sparse as enough. Yeah. So just before, we only focus on one receiver. So how can we combine these 4 receivers or n receivers? It is very intuitive that we have got 4 dictionaries separately, and we can have 4 measurement Y and 4 sparse vectors X. Here, the sigma is the Gaussian noise, white noise. And our proposing is, because one target on the 4 receivers, the dictionary items are different, but these X will share the common support of the vector. Yes, and this gives rise to the following optimization, which means if we put X, a really long vector, consisting of the 4 vectors from the 4 receivers, X1, X2, and X3, and X4, and we could solve this norm to 1 problem of that vector X, which means is this one. And roughly speaking, it's like this. For example, the green one is 1 receiver, the dictionary and the sparse vector and the measurement. And suppose, so this vector composes of 2 items, which are these two. And the red one we have 2, the yellow one we have 2, the blue one we have 2, but these 2 are all different, separated. If we use only single dictionary estimation for 1 time, and we do 4 times, and then we estimate this grids, it is there are many ambiguities. For example, here, according to this dictionary, we see the 4th and the 8th, 7th is where the target is. But for here, the grids are different. And how do we solve this one? So we put all the vector into 1 column, and we put all the dictionaries into the diagonal matrices. And we also put all the X vectors into 1 big vector. So our proposing is, if we use the norm to 1 constraint on the whole X, we could observe that the same number, the same grid would be the most powerful X, which means that constraint can help our estimation problem more in an optimized way. For example, so this one is ambiguity, but for the norm to 1 estimation, this ambiguity will be eliminated because of the norm to 1 optimization. So we could regard it as a regularization, so that these 4 vectors would share the common support, which is the force. Yeah, and here's the result for the single dictionary signal recovery problem. So, and the ground truth is the red one. The ground truth is the red one, which is the red star.
What's the axis of the plots?
Here, the axis is the number of grid.
Okay.
Yeah.
Is that range or time?
No, not range. Just which grid do we
okay,
know?
the grid index.
The grid index. They are 2500. but we only use 500 measurement samples. Yeah. So we could see from this 10 dB scenario, this algorithm is okay, but for the 5 dB one, you see there are so many ambiguities here, which is why the joint processing could optimize this problem more. And here is the joint processing. So we utilize the norm to 1 optimization to the whole X. And actually we combined 4 receiver vector into 1 big vector. So that we can see that, yeah, exactly it is what we want. Yeah, so it could be seen that the estimate of the grids, it would be more efficient and effective if we use the joint processing framework. And here's the summary. So first, maybe in the simulation results, we showed that multiple targets, Doppler-only localization, that one is feasible. And the second is joint signal processing method may fit the requirement to enhance the localization accuracy, or fits the requirements that we could do super resolution of the frequency. Yeah, yeah. I guess this one can be applied to the. It's more like the phase-sensitive processing. And there will be some future work. First, the optimization needs to be faster, and the convergence rate and effective denoising, we should do the theoretical analysis. And the second is we implement this method into experimental data. And we investigate the effect of different grids chosen. What's the resolution of the grid? Or is the uniform grid more suitable to this problem, or non-uniform grid was suitable to this problem more? And the next is it possible to use the grid list dictionary for this optimization? Yeah. Thank you. That's all.